Hello everyone and welcome to this short video presentation on the paper Beat and Downbeat Tracking in Performance MIDI using an end-to-end transformer architecture. My name is Sebastian Murgul and I'm co-founder and CEO of the company Klangio, and this paper is a collaboration between Klangio and the Karlsruhe Institute of Technology, where my co-author Michael Heitzmann is supervising my PhD. So first of all, beat tracking is a key task in music information retrieval, which is important for automatic music transcription and rhythmic analysis of musical signals. The goal is to find out the positions of beats and downbeats in musical input, which can, for example, be an audio signal or a MIDI signal. In terms of audio, there are a lot of methods out there. And in terms of MIDI, there are less methods out there, and it's a little bit more difficult since you're lacking a lot of emphasis and expression, which you lose when turning audio into MIDI. But you also have the advantage that MIDI is purely symbolic, which means it is less noisy, easier to augment, and there are ways to synthesize MIDI. The results of the beat tracking, the downbeats and beats, can be used for figuring out the underlying bar grid of a musical piece and are also important when it comes to finding the meter and the tempo of a song. Here we present a new approach using an end-to-end transformer for beat tracking in a symbolic signal. The model we are using is based on the T5 transformer, which is originally proposed for language translation tasks, and we are using it since we are interpreting the problem of beat tracking as a translation task between the MIDI language and the beat language. Therefore, our input is MIDI-like text tokens, and our output is beats and downbeats encoded in text. Speaking of encodings, we experimented with different complexities of the input and the output. First of all, we have one version with only onset information with pitch and time stamps. On the target side, we have a beat counter which counts from 1, 2, 3, 4, 1, 2, 3, 4 in a 4/4 bar. But we also have the time token here. And in version 2, we not only have onsets on the input side, but also offsets. In version 3, we also add velocity information. In version 4 and version 5, we replaced our beat counter token with a dedicated downbeat and beat token. And we experimented with one version with also velocity information and one version 5 without velocity information. Besides the complexity, there are other parameters to experiment with, for example, the temporal quantization and the length of our segments. For our experiments, we used 4 different datasets. First of all, the AMAPS dataset, which is a piano dataset with aligned MIDI and rhythm labels. Our second dataset is the ASAP dataset, which consists of classical piano performances with a little bit more expressive timing than the AMAPS dataset. Our third and fourth dataset are guitar, or for the guitar. First of all, we have GuitarSet, which is really popular in the automatic music transcription. Unfortunately, we only have the time signature 4/4 in this dataset, which makes it kind of boring. Therefore, we added the fourth dataset, the Leduc dataset, which consists of jazz guitar transcriptions, where we use the approach presented by Riley et al. To automatically align the Guitar Pro transcriptions, which you can buy on the author's website, with the original audio, and we not only align the notes, we also align the rhythmic information in terms of downbeat and beat positions. Since we have now our databases, we can use these data and prepare it for our training. First of all, we extract the notes and the beats. We split into overlapping segments of the same length, and then we apply some data cleaning because we don't want any segments with less than one beat in our dataset. Then we write everything into a CSV file, which is then loaded dynamically during the training. During the training, we apply additional preprocessing in terms of data augmentation. The data augmentation we use are pitch shifting and temporal shifting and scaling operations. We then apply quantization to the times for the notes, and then apply our encoding and tokenization scheme in order to claim our dataset, which we then fed into our model. In our ablation study, we found out that the encoding is really important and has a significant effect on the results. And in general, we can say that the more information you have on the input MIDI side, the better. And you also want less complexity on the output side. Therefore, version 4 leads to the best result, which consists of onset, offset, and velocity information on the input side, and downbeat and beat token on the output side, so no beat counter. For the segment length, we found out that 10 seconds is a good balance between context and model capacity. And to our surprise, the time quantization has a really high effect on the downbeat accuracy. You want broader time quantization, which leads to a little bit of unprecise results, but they are getting a lot better for the downbeat, which might be caused by the imbalance of the data itself. By applying data augmentation, we were able to leverage the beat F1 score. The shifting and scaling truly improves the results here. And we combined all of our results and formalized the resulting model and compared that one with the state-of-the-art approaches. First of all, Beat This, which is an audio-based method, and our second approach is the hidden Markov model by Nakamura et al., which is divided into a pop and a classical model. Our third model is the PM2S by Liu et al., which is a CRNN neural network. In our experiments, we were able to outperform the other symbolic baselines in almost every score, but of course the audio-based beat tracking still leads to better results, especially for downbeat detection due to the more expression and emphasis that you find in the original audio performance. So, to conclude, we presented an end-to-end MIDI-based beat tracking transformer, which is interpreting the task of beat tracking as a translation task, and we showed that this is highly effective and also generalizable across different musical instruments. And while outperforming other symbolic instruments, our approach still lags behind audio-based models, but this is kind of an unfair comparison, of course. In future work, it would be really interesting to leverage the advantage that we have in the symbolic nature of MIDI by creating a procedural data generation pipeline for the training, where we generate a kind of unlimited data set on the fly during the training. Also, combining this beat tracking approach with a beat-based quantization method would be an interesting approach to MIDI to score conversion with some amount of control over the results, and also adding more instruments and adding the multi-instrument case would also be really interesting. So thank you for listening to my short talk. Unfortunately, you can't visit our poster anymore, but you find a link to our full paper on archive in the description, so feel free to check it out and connect with me if you have any questions. Bye.